uh, I'm really indebted to the organizers for having invited me to present my views or delusions in mean field theory. And as I learned from Professor Frankel's lecture, it is to be seen whether you will be grateful to the organizers at the end of my lecture for having invited me. And speaking of learning, of course, this is not the only thing I learned from Professor Frankel's lecture, and from whom actually, both in this workshop and the preceding one, I learned a lot. I've been learning a lot during these workshops and during my stay at Newton Institute. I'm really very grateful to the director and the organizers of the program who have invited me to stay here for a long period. And again, speaking of learning, I come back to this first title of my presentation, which is in Latin, Ex multis unum. And the reason why I am saying this is not just to impress you, but because I remember once giving a lecture, and I was asked a question at the end of the lecture. And during my lecture, I had mentioned an Italian old professor from the last century, and I've quoted his work. And there was a member of the audience, pretty distinguished member of the audience, who said, "May I ask you a question?" Yes. "How do you pronounce?" I never pronounce the name. "How do you pronounce the name of this professor?" And I pronounced the name. And then he said, "Yes, this much I learned today." True. And then I said, "Look, now next time I'll start the lecture, I will insert some Latin or Italian motto, and I'll pronounce it and say, so somebody at least has learned something." And this is maybe the most I will teach you today. Well, now be a little bit more serious. I had to be start up again, since you are already thinking of lunch. So I had to impromptu. I had to start this joke, but it is true. I mean, all this happened to me. All right, averages and ex multis unum again. Mean field theory, there is one way, very nice and simple way of describing mean field. It is art, somebody would say, the dark art of making averages. And of course, let us do it properly, and let us hint at different flavors of doing these averages. In fact, there are several ways, and I'll try to present at least two, if time permits, three of these flavors, hoping that they don't melt up in our ice cream cart. But this is the start. So what averages are about? Well, they used to predict transition between different collective molecular arrangements, mainly driven by changes in temperature. I'll be more concerned in this talk with thermotropic phase transitions and phase arrangement. And again, I mean, seen from a different perspective, they, I think, constitute a possible theoretical foundation of continuum theory for soft matters. And the idea is they, for example, suggest what kind of order parameter rooted in a kind of microscopic understanding has to be proposed. There are many different ways, but maybe having a kind of first approach via mean field theory could suggest a more appropriate way of introducing order parameters, mainly order parameter tensors in my approach, which might surface at the macroscopic level, but being rooted in the microscopic realm, they will bring into life the signature of their molecular origin. And the third hope this is more a hope than anything else, they can really help bridging scales between these two different levels. We have seen in this workshop, I mean, I think the workshop is entirely based on this deep and illuminating interplay between molecular arrangement and continuum theories. And we've seen in many lectures, at the end of the day, you need some kind of continuum understanding, because this is the life we live. We live in this world, which is at our length scale, and we need to get some, maybe crude, but effective information what happens at this length scale. And of course, all we learn from the microscopic world has to be translated and transported into the macroscopic level. And we know that the most effective signatures of macroscopic phenomena are those which are actually inherited by microscopic features. And there are many ways and many avenues to make microscopic detailed features to be manifested at the macroscopic level, provided we have the right eyes and the right tools to capture them. This is a bit philosophical, but anyway, there is a rigorous formulation, I think, there are several different equivalent rigorous formulation for mean field theories, and of course I'm a little bit biased, so I'm following this one. But I think there is a room to interest mathematicians on these fields. And at least, I mean, this is the most ambitious hope I have for this lecture, to convince you that there is, even if it is a very old subject, very successful in many cases, my hope is to convince you that there is still room for mathematical rigorous inquiries in this field. And these inquiries, we know by experience, that will always lead to better understanding. So this is what mathematics is about. It is not about computations. I learned once that the best definition of mathematics is the art, maybe dark art again, of avoiding unnecessary computation. All right, so let us get it straight. The idea is that there are these interaction potentials. We have seen tons of them already in this workshop. But the main idea of a mean field theory is to start taking averages. And the first average you take is relative to the intermolecular vector. So again, it is crude, and you miss something. Whenever you make averages, you miss something. For example, budget discussions are in order and are based on averages. And of course, maybe averages get reduced, but everybody, in that case, everybody loses. But there is someone who loses more than someone else. But anyway, the problem remains that you need to end up with something which is manageable. And what is manageable in this case is produced by averaging over the intermolecular vector. In such a way, you produce what is called the pair potential. There are means of injecting into these averages some steric effects. Dispersion forces, for example, have been invoked many times. These are mainly attractive forces, but they can be, I think they should be somehow corrected by some kind of molecular or steric hindrance. And this can be done, and this can be actually properly built into the average process that we take. But anyway, these are kind of separate avenues. The main avenue I want to follow today is based on the idea that somehow this Hamiltonian has been given to you, and this Hamiltonian depends only on the, say, state of the molecule, of the interacting molecules, of both molecules that interact, and the interaction potential does not depend anymore on the relative position in space of the molecule. All right, rigid molecules, of course, have been already used many times. In this case, H is a function of the relative orientation only. In general, if the molecules are flexible, then the Hamiltonian that I'm considering depends also on the conformation of the molecule. So, theoretically, this is what our application H does. It assigns to a pair omega omega prime of states a real value. So omega and omega prime, they live in this state space, and imagine, think of omega as the orientation of a molecule, of a rod-like molecule, for example, or of a platelet, and if it is more flexible, then there is, for example, a variable angle between the two moieties that constitute it, etc. You can make this as rich as you wish, but again, mathematically, it's just a space in which omega and omega prime live. All right, you need to require that the Hamiltonian, since the particles are indistinguishable, the Hamiltonian is symmetric and the exchange of the two particles, and you need to imagine that there is a kind of effect on this manifold which is exerted by the rotation of all the systems. So this is sometimes called frame indifferent. Whatever you have constructed cannot depend on the choice of the reference frame. So you need to work out the action that the rotation group exert on this manifold, which is a change of state. But the change of state has to be ineffective as long as the interaction is conserved. All right, there is symmetry, of course. You might imagine that there is a group of transformations into this space which affects the state but doesn't affect the interaction. A platelet, for example, you take in the previous lecture, you take a platelet, you reflect it through a plane, symmetry plane going through the center of the molecule, then of course the platelet is different because points have been changed into the platelet, but you believe that the interaction has not been changed. This of course constitutes a symmetry group, and you want the interaction to be symmetric, unaltered under the effect of this group. All right, we envision this as a measurable space because eventually you want to put distribution functions on the space, and you want to know what is the probability of finding one molecule in a given state in this, well, large meaning of the word. All right, then it means that you need to, you make it compact in order to introduce this measure, and then you introduce an appropriate measure. I'm saying here only appropriate. You need to be very careful, for example, on if you want to represent the rotations, and if this is simply, this manifold is just one way of representing the SO3 group, then we know that there is only one measure which is invariant under rotations. Of course, this is important because you want that one measure, one patch, which has one measure on the, say, S2 disk, has the same measure once it is rotated. And there is a famous theorem by Hart that says that there is only one measure which is invariant under the action. So you need to be, I will not go into many of these details, but I want just to give you a flavor, again, of what can be done properly, I think, in order to find the ambient for this theory. All right, examples. I don't want to be too abstract. This is the rod. Well, in this case, this is the appropriate symmetry group, DH infinity H, a platelet, we have seen many of them, and this crescent, this V-shaped, we have seen already a V-shaped molecule making its entrance on the scene. Well, of course, these are three different symmetry groups, and of course, as we proceed along this axis, these groups become richer and richer, and of course our job becomes harder and harder. All right, there is a general class of Hamiltonians we shall actually confine our attention to, and it's called the class of bilinear Hamiltonians. And the idea is that such an Hamiltonian can be represented as a bilinear form in appropriate molecular tensors. All right. as I said, it's a dark art. I'm just starting speaking this dark art language. But let us be a little bit more precise, and let's go into where I think the most glorious of cases, which is Myers-Zaupe. So in this case, again, we introduce an explicit representation of this Hamiltonian H in terms of another Hamiltonian, which is H hat. This, of course, says that H hat is a function of the pair of the two tensors Q and Q prime, and these are the famous uniaxial tensors which can be associated to the axis of symmetry of the molecule. Right, this U naught is simply a scaling energy, and in this case, omega, which was our state space, is simply S2 is the orientation, what I call the orientation sphere. Of course, there are means to introduce these quantities, and these means, of course, are based on symmetry. So you can easily prove by just making those requirements, which were very abstract and general a minute ago, to make them concrete and real. Then you can prove that in this case, actually, this is the only molecular tensor that is compatible with the symmetry. So this is a kind of a nice exercise. You put together all these ingredients, and at the end of the day, you say, all right, this is the molecular tensor I can use, at least in the quadrupolar case, meaning that it is a second order, second rank tensor. Of course, I can construct plenty of higher rank tensors that would share the same symmetry and which would be equally admissible for my general bilinear expression, but I promise to keep things simple. Though the theory works perfectly right, no matter how many tensors you construct based on symmetry. So symmetry requires a number of tensors you can use. I call them molecular tensors just because they are motivated, justified in terms of molecular shape or molecular symmetry, molecular property, whatever you like. So this is, and indeed, this in this case is the most general quadrupolar energy that you can come up with. And of course, there are others, but they would invoke higher rank tensors, and so higher types of approximations, speaking in terms of dispersion forces. This, for example, is what the dispersion forces approximation requires, nothing more at this level. All right, Straley model for biaxial nematics, it is just the same. You just use the fact that this is a symmetry now. You restrict your attention to only quadrupolar tensors. You make the symmetry work for you, require bilinearity. You make all the ingredients again in the cauldron, and all of a sudden, this is what you get. This is the most general, again, interaction you can get. And these Q is the same as before. This is one of the axes, and B is the new player, which is actually the biaxial player, which of course was absent in the previous case. And you go back to Straley's model and immediately realize that the complicated formula, which is in Straley's model, can be easily replaced by this. Freiser's model, which is a sub-case, which was the starting model, is obtained as a special case when lambda is equal to gamma squared. And this lambda equals gamma squared in this theory will play, in this example actually, will play a crucial role. We'll come back to this, I hope. All right, you can again complete the exercise for the CT2V molecules. Again, this is a crescent, and of course it is just the same, but there is an extra symmetry, and this extra symmetry already makes it manifested at say the dipolar level, because symmetry allows for a dipole moment which is along E2, and the most general dipolar contribution, which is even lower rank than the quadrupolar we have considered, would introduce this. And of course, this means that there are other order parameters that will be produced by this interaction. As I said, I have not yet introduced order parameters. This is only something which is based at a molecular level. My next task will be to extract appropriate order parameters just from this description. All right, but with one particle we do nothing, and so we need more particles, and we go then and consider a system of n identical particles. In this case, we need this vector omega, which has n entries, and so we need we need n copies of this space. So this n to the n simply means n Cartesian by itself n times. So this is simply n copies of the n field, and we introduce this notion of interaction set. So we have a pair ij of interacting particles, and this is an oriented pair by definition. So all the time I is always less than j, and I simply say that ij is a pair that enters, that is a part of the set if I interacts with j. And I call n the cardinality of this set, so the number of pairs which are present, interacting pairs which are present in the system. It's a very simple combinatorial exercise to prove that n is always greater than the ceiling of n over 2, which is by definition the least integer, which is larger than n over 2. All right, then we start constructing ensemble Hamiltonian. Again, this bold omega is now the state of the ensemble, the state of the system. Omega has n entries, one for each particle, and it tells me precisely which is the state of each particle entering the system, and this is by definition the sum, because I consider only exchange interactions, two particle interactions, so it is the sum over the interaction pairs of the exchange Hamiltonian. All right, I take the Boltzmannian statistics, and I introduce, now this is the ensemble Hamiltonian, I introduce the distribution function of omega. Beta is the usual Boltzmann factor, T is the absolute temperature, and this is the partition function now. Again, I now integrate over that measure that I introduced, and I integrate the exponent of minus beta, the total energy stored in the system, and I can easily construct by using Boltzmannian statistics, statistical mechanics. I can introduce the ensemble free energy, which is defined in the usual way. This is the ensemble internal energy, which can be derived strictly and directly from the ensemble partition function Z, and this is the ensemble entropy, which has a canonical definition, and of course combined together they produce a free energy function, which can also be obtained directly from the partition function. All right, this is what I mean for ensemble average. This, for example, would be the ensemble average that produces the internal energy. It is integral over omega to the n, these n copies of omega of this function, and again this bold omega reminds me that this is a vector of states, and this is just a shorthand for the ensemble average of any function f, which, as is made clear here, is a function that depends on the collection of states. All right, it is useful, of course, to consider the per particle versions of these of this function, and I simply divide these global ensemble thermodynamical quantities by the number of molecules. And now I start constructing the mean field idea. Mean field idea is an approximation, and in an approximation you replace something you don't know with something you hope to know, and you still hope that the replacement has a good degree of fidelity. And now how can we make it work in this case? All right, this replacement must take place somewhere, somehow. And there are two ways of making this replacement. At least I see two ways of making such a replacement. One is at the Hamiltonian level, and it is part 1 of my lecture, and the other would be at the distribution function level, and I hope it will be part 2 of my lecture. Now, what we do here, we simply replace one Hamiltonian with another Hamiltonian. And when it comes to replacing Hamiltonians, then one has to know what is losing and what is gaining in the replacement. And there is this well-known Gibbs-Bogoliubov inequalities that tells you that whenever you replace one Hamiltonian with another, these are ensemble Hamiltonians, but the ensemble Hamiltonians, of course, are generated by the exchange Hamiltonians. When you replace one with the other, which have been obtained by using two different Boltzmannian distributions, meaning that they have been generated by two different exchange Hamiltonians, of course, you produce two different, for the same temperature, you produce two different free energies. Well, they are in this wonderful relation. Good. How can we make any use of it? Yes, we can, because this is precisely what the mean approximation does. Why don't we replace then our interaction energy with something which depends on a field? It is parametrized in a field, which is going to be called the mean field. All right, this is a field which every particle produces and feels. There's a kind of self-contradiction, as we heard in the previous lecture. So, and this is precisely what we do. We replace H with the one particle Hamiltonian H naught, which depends only on the state of the single particle, but it is influenced by all other particles via this ghost field. And the ghost field is produced and felt by all particles, so it acts at the same level with all particles at the same time. So then just to make our notation a little bit more compact, I call Q, which is very similar, of course, in the font to the Q tensor that appears, molecular Q tensor that appears in the Mayer-Zaupe theory. I call the collection of all molecular tensors that you want to use. For example, in the Mayer-Zaupe case, Q is a very poor collection, only one tensor. In the Straley model, Q is a little bit richer. There are two molecular tensors. In the C2V model, then there is a vector and two tensors. So in general, you might have tensors of different rank in this collection. And this is just a very shorthand to indicate this H hat function, which is now a function bilinear in all entries of all the collections of molecular tensors. Omega prime is a state of the other molecule. Omega is the state of our preferred molecule. We need always to identify ourselves with somebody. And so we identify ourselves as omega. Omega prime is the other molecule. And that Q prime is simply Q in the other state. So it's a collection of all tensors in the other state. All right, and then this would be the explicit representation of H in terms of H hat, just to remind yourself of what we are doing. Now, how do we define this replacement, H naught for H? Well, the idea came from, I think, a very nice paper, which I read and enjoyed a lot, by Peter. And Peter said, all right, this is a way. This is a way to introduce the one particle Hamiltonian. Now, the one particle Hamiltonian depends on something, which is, and this something is a field, is a mean field, which is, as I said, produced and felt by all molecules. And he simply said, all right, you freeze the first molecule, and you take averages relative to a particular one particle distribution function that I will introduce in a moment, and to avoid the double counting, you do this. You just subtract the double average on both entries. All right, what is R naught, rho naught? Well, rho naught, of course, depends in the Boltzmannian fashion on H naught, and Z naught, of course, is a normalizing factor. It is a partition function. Of course, there's a price to be paid. As I said, omega Q, big Q is not any tensor. Actually, in this case, it's a collection of tensors. It's not anything you can come up with at your will. it must obey this property. As I said, is a mean field. So it is a field which is obtained by taking average into this rho naught, into this particular distribution function, then that depends on h naught of the collection of all tensors. Again, you produce a collection of tensors here by taking averages of a collection of molecular tensors. So the same number of entries which is hidden in Q would be present in big Q. Of course, strictly speaking, from the mathematical point of view, this means that simply means that H naught was defined above in an implicit way. So this is not an explicit definition of H naught. It looks explicit, but it is deceiving you because it is not explicit. It is implicit because you know rho naught, which is the distribution function which is used to make these averages, is a function of H naught itself. So, of course, once you have made such a definition of H naught, we'll see in a moment how to compute it in a number of simple cases. You get a function of this new collection of tensors, and you can pretend that it is a function defined everywhere in the whole space where the collection of Q lives. And for an extended H naught, you can compute, again, this could be faked, but we'll see in a moment that it isn't. You can compute via this definition now. It is not a theorem, this is just a definition. You call this the one particle free energy function that, of course, depends on Q naught. You simply start from H naught, you extend it to the whole space, and you define this quantity, which is a function, and you call it the one particle free energy. And then there are a number of properties of this function. If you compute the average of relative to H naught of this quantity, now this is a tensor because you are differentiating a scalar relative to this collection of tensors. Actually, this is a collection of tensors. You get df naught dh. So there is this nice correspondence. This is just a computation, which is justified only if you have taken the liberty of extending H naught and Z naught to the whole space. And then this means something very interesting. It means that if such an average is 0, then you can prove it, then the Q that makes this 0 actually satisfies the self-consistency condition. And this is, again, in turn, equivalent for what we have seen a moment to the requirement that the collection of Q makes F naught stationary. So the critical points of F naught are identified automatically with the point which obeys a consistency condition, and this in turn can be characterized in terms of this average. Well, then you, at least for the Q that makes sense, of course, we have seen a moment that not all Qs make sense, but with this trick of identifying the stationary point of this extended free energy, you can identify those Q, and this is just a criticality property. You identify the critical points of F naught, and for those critical points of F naught, you can compute all the thermodynamical quantities, the ensemble quantities, because they make sense. Those are the self-consistent Qs. So you compute all your machinery, and again, you can compute the one particle distribution function, and here comes the replacement. What you do, all right, you simply say, only for the self-consistent Qs, I replace H with H naught, rho by rho naught, and so forth. So my prime here now becomes zeros, because this 0 here reminds me that I'm just considering one particle distribution function. And then the Gibbs-Bogoliubov inequality takes this form, which can be a little bit massaged, and it is just the same. I mean, you can check, I'm not fiddling. this F naught, which is one particle free energy, is greater than equal than the free energy, which we don't know, of course, plus this correction term. So it means that we are, in replacing F with F naught, we are making this error. So we can estimate the error in a way. All right, in the Bogolyubov language, all these ideas come from Bogolyubov papers. This is a trial Hamiltonian. Can be done, of course, this trick can be adapted in different circumstances, but in the mean field case, this is what we do. And then, of course, you need to prove something more. And you prove this inequality, which is valid only for H bounded, by possibly rescaling H if the only requirement is for the parent H, the one that originated everything, is only the boundedness requirement that matters. Under this assumption, then you can prove that this is always greater or equal than 0. And if you go back to the previous inequality, now you estimate this error, and you simply say that this error is positive, so it means that your replacement is always above the original and unknown free energy. So this is now your minimum principle. It becomes a minimum principle because it tells you that you need to be always, you are always above, for any given beta, you are always above the true free energy. But of course, this makes sense, this F naught makes sense only at the point that make a Q, that makes it stationary. So the Q that matter are those that make F naught stationary. So the idea now is very simple. The conclusion is very simple. What you need to do is to find, in order to get the best approximation, you need to find the least critical value of F naught for each beta. And this becomes a computable criterion. All right, of course, there is a problem always, there is a but. There is no guarantee that the global minimum of F naught exists. You see, when you freeze the constraint that F naught must be stationary, and you look at F naught extended into all space, there is no guarantee that there exists an absolute minimum. This could be an unbounded function. But it doesn't matter, because by the theory that I presented, the only thing, which is Bogolyubov theory, the only thing that matters is the least stationary point, which always exists. All right, there is a little bit of technicality here. You can compute the Hessian form of F naught and compute it. This is a general formula. You compute it as a stationary point, and then you realize that you can prove, actually, that if you can prove this formula, and then if you introduce a splitting, and this appears at the beginning as a bit arbitrary, but you can, for a moment, just bear with me and imagine that you can isolate a negative component from a positive component, and positive means attractive in this language, negative means repulsive, and the definition is the following. I call Q minus repulsive if this form, which is a quadratic form, is negative definite whenever the average is 0. So whenever Q makes F naught stationary. And then if Q minus is repulsive, I can prove that then this quantity, by using the previous inequality, that this form is negative definite for all critical points of F naught. So this means that repulsion introduces concavity. That's, the message. And we'll see in a moment that there are ways to identify the Q minus, the repulsive order tensors can be identified and related to the molecular repulsive tensors in a way that is made a little bit vague here, but essentially you can always identify a repulsive order tensor as the average of a molecular tensor which doesn't wish to be aligned with its counterpart in the other molecule. So repulsion in this case simply means dissimilarity. If in the ground state these two vectors do not wish to stay to be similar, then we call them repulsive, and eventually you can prove that a repulsive molecular tensor generates a repulsive order tensor, because these, again, as I said, these averages are nothing but order tensors. All right, then there's a very classical result called mountain pass lemma, which says that if this is the case and if this function is negatively coercive, meaning that when q minus goes to infinity, when q minus goes to plus infinity norm, this goes to minus infinity, then there is a unique point at which this function attains its maximum. It is a very old result by Courant, and then this means that you can find a unique solution to this problem in q minus. So the idea is that repulsion in this case is very useful because you can always solve for q minus this equation, which means that for every given q plus and beta, you can always, in principle, find a mapping that delivers q minus as a function of the attractive part. So in a way, this means that repulsive order tensors are enslaved to the attractive ones. All right, and then you simply now enforce the criterion of least subtle, and again, this goes back to Bogolyubov Jr., 1972, and then you can easily prove that if you want to extract all local stability information from this reduced free energy, which is, you know, is the energy that you compute once the q minus tensors have been enslaved to the attractive ones, then the only thing you need to do, and this is very useful from the numerical perspective, then the only thing you need to do is to count how many negative eigenvalues are in this Hessian form. And the negative eigenvalue must be at least equal to the repulsive dimension, namely must be equal to the number of independent repulsive tensors. And so this gives actually an effective criterion to forget all about this theory. Theories are usual when you can forget about them and extract a practical criterion. Nothing is more useful, I think, was Goldman say than a good theory, practical than a good theory. And this is precisely what this theory does. You forget about everything. You go back to your original F naught, extended through all space, and you compute the eigenvalues of the Hessian form of this function. And now, if you have properly identified the repulsion dimension, the only thing you need to keep in mind is this number, 2, 3, 4, whatever it is, and you count the number of negative eigenvalues, and you say, all right, if the number of negative eigenvalues is equal to the repulsive dimension, this is stable, because it is a minimum now of this function. All right. Example, again, we go to the biaxial case. This is just a very short and quick vision. Now, as I said, in this plane, which is a gamma lambda plane, this parabola is essential, because you can prove that below this parabola, this is a parabola lambda equals gamma squared, below this parabola there are indeed repulsive interactions. And actually there's a very nice exercise which I did once, that if you take Streley's interaction based on excluded volume, you can map all excluded volume Hamiltonians into points below the parabola. So meaning that, as I should, hardcore platelets interact via repulsive interactions in this sense. So hardcore in this case is repulsive in precisely the sense that I made precise a moment ago. All right, these are the order tensors. S and P, S prime and P prime are uniaxial and biaxial order parameters. These are the phase order parameters, because Q describes how the main long axis is oriented, and this is sometimes called the biaxial tensor. And these are the biaxial order tensors because they have a molecular origin, and they tell us how the B biaxial molecular vector tensor is actually aligned. So this is another way of introducing the 4 scalar order parameters, which are typical of biaxial interactions. All right, and now there is a way to identify repulsion in this case. And the easy way is to introduce what I call the modal decomposition of this interaction. You can always write it as a sum of 2 seemingly dispersion forces interaction. So this is interaction between 2 similar tensors. These Q plus and Q minus are simply linear combinations of the Q's and the B's. And this is a very simple exercise. There is only one way to produce this decomposition. And you prove again that whenever you are below the parabola, this is negative. So one of these 2 is repulsive. You don't know which of the 2, but one at least is repulsive. So this means that you identify Q minus, which is now the repulsive order tensor, and you can be sure that this is the case. Okay? Now you represent explicitly Q minus, and you describe that it depends on 2 or scalar order parameters. So the whole variety of repulsive tensors can be represented by 2 scalar order parameters. So it means that M minus is 2 if lambda is less than gamma squared, or equal, and it is 0 if it is greater than lambda squared. And then by using this machinery, you can easily identify the phases and their stability. And this is what comes out of this. This is actually the case that was first examined. It is the case gamma equal to 0 and lambda between 0 and 1 and 1/3. And this is, for us, is important because we then proved that this actually, the properties of this phase diagram are universal. So qualitatively it is the same for all points in the admissible parameter space. All right, here is the isotropic uniaxial transition, which is first order. Blue means here first order transition, red means second order. The novelty here, there are 2 novelties, I think. One is that this point where blue blood and red blood mix, but this is a tricritical point. It is a point where the transition from uniaxial biaxial becomes first order. But on top of it, there is a full line here of direct uniaxial, isotropic biaxial transitions, which of course happen to be first order. How much time do I have?
Well, taking into account that you started a little bit later, about 10 minutes.
10 minutes, all right. It would suit me. So this was one way, a replacement. You replace Hamiltonians with Hamiltonians. But there is another way, and the other way is actually stems from the fact that there are other ways of making averages. And one other way to make averages is by manipulating the probability density. So the idea is that we go back to that multiple body probability density, and we impose again a replacement. We replace it with the product of the same function evaluated at the different variables. This simply means that the probability of finding one molecule in a state is the same in one given state is the same for all molecules. Again, and then the product of these probabilities densities is just our new. All right, then if you assume that this is normalized, omega is the same omega as before. If you assume that this is normalized, then also the product will be normalized. And then you start by a different approach, and you say, all right, I define the ensemble free energy functional to be a functional now. It's not a function, but it is a functional of a distribution function. And I define this in this way, where H, of course, will be defined. So I take the ensemble Hamiltonian, and I integrate it over with this weight, and this is the entropic part. So this is a classical definition. And actually, I go back to my previous definition of ensemble, Hamiltonian, and I express it in terms of the exchange Hamiltonian, and this is what I get. It's very simple exercise. Again, n, which is the cardinality of the interaction set, surfaces one more, and this is number n, the total number of particles present. And then when I go to the per particle functional, I divide by the number of particles, and I get this new guy here, which is defined as the ratio between 2n over big N, and it is a coordination parameter. It tells you essentially how many particles interact with a given particle on average. And this is coordination parameter, which of course goes from 1 to n minus 1. It is 1 only when one molecule interacts with only another one. And of course, it is maximum n minus 1 when each molecule interacts with all others. This would correspond, of course, to the maximum cardinality of the interaction set. So you needed to rescale your exchange energy in order to make it work. All right, again, Mayo-Zaupe example. This is, again, we have seen this already, our compact representation. And of course, there are many other avenues which have followed precisely the same steps. And these are just three recent and less recent citations. And this is, again, my representation of Q. And now the problem is, this is a functional, and I want to minimize it. So I already made a replacement. The multiple particle distribution function has become a single particle distribution function, and you can prove that actually this is a minimizer. This is a minimizer of the previous functional, but again, there is something odd going on here as well, which should, in a way, be connected with self-compatibility. And the self-compatibility remanence here is given by this definition of H rho. I define rho in terms of a function H rho, which is in turn a function of rho. So this is a formal solution to the previous problem, but if I look into more details, this actually is a fixed point problem for rho. So this is a mapping that gives a function H rho in terms of another function H rho. So it is a kind of operator. It goes from the space of all distribution functions into the space of these Hamiltonians. But of course, this is a requirement that tells me that the original rho must be equal to this function of H rho. And of course, this identifies a problem which is called a fixed point problem. All right, how to solve it? Well, one way of solving it is to parameterize H rho in precisely the same way we had parameterized it before. And this actually offers the connection between this approach and the previous one. Eventually, the two approaches are completely equivalent because even if expressed differently, they amount to the same problem of finding the Q's that obey a fixed point problem. All right, there are advantages in using this formalism, but since my time is over, I will skip the advantages and I'll simply speak about something I'm trying to do in my stay here, and the idea is to exploit the full steam of fixed point theory and apply it to phase transitions. I mean, one perspective that I have at the moment, or maybe one delusion that I have at the moment, is that actually phases can be identified with defects. in a way, in an appropriate functional space. And of course, a charge can be applied, associated to these points in quotation marks, and the topological degree theory tells us, or helps us identify how many of these transitions are possible and where they could be. Of course, this is a kind of long-term project. At the moment, I've been able only to tackle, to some extent, to a degree, I should say, the Meyer-Sauper theory. So revisiting the Meyer-Sauper theory in this language, which is inspired by the fixed point theory. I think that this is more than enough, but I think I need to thank, well, all the people at least have bugged with my questions and from whom I've really learned a lot in the real sense of the word. Thank you very much. Sorry for being a bit late.
Thank you very much indeed, Epifanio. I am deeply sorry again. So I'm sure that we will discuss these matters later on and for more than one day. But now we have just time for one quick question.
I'm trying to translate these ideas into other parts of statistical physics, where Gibbs-Bogoliubov is used all the time. And there, it's a matter of choosing an intelligent reference system or trial system, your H prime. Is what you're doing telling us how to do that? And nothing more than that?
Yes, in a way. This would be a kind of reductive way of presenting, yes.
You know, because Bogoliubov himself showed how to derive Curie-Weiss theory. That was one of the first applications. And in liquids, one tries to choose the simplest possible reference fluid for dealing with, which doesn't seem quite in the same spirit as you have.
Well, what we do here with H naught, and this actually is one way of interpreting mean field theory within that landscape. So, yes, this is what we are trying to do. Of course, there might be other ways, other H naughts that could be, this in a way is a traditional way, but you see that these two avenues, the traditional avenue to mean field and this Bogoliubov type of approach eventually converge to one and the same answer. But the theory, Bogoliubov theory is much richer. You could, in principle, find different and more adequate replacement for H naught. But the spirit is precisely that.
I fear to say that this is the end of the morning session.